A moving average smooths noise but lags and cannot estimate hidden velocity. FilterPy's predict update cycle combines motion and measurement uncertainty to recover position and velocity from noisy readings. You'll build and run a constant velocity Kalman tracker that estimates position, velocity, and 1 sigma position uncertainty from noisy position readings. I'm Professor Pi, teaching AI foundations with simple Python. Kalman filtering is useful whenever your sensors are noisy, but you have a simple idea of how things move. It blends a motion model and measurements so you get cleaner numbers, plus an uncertainty estimate you can actually trust. We'll first make the moving average lag visible, then build a tiny FilterPy Kalman filter, run it over measurements, and finally score the improvement against a synthetic ground truth. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. So we start with a simple smoother to make the lag obvious. This snippet generates a tiny noisy position track and shows how a 3-point moving average falls behind the true motion. NumPy creates true pause, adds a patterned noise C, and uses np.convolve to compute the moving average. The code prints the raw last reading, the smooth last reading, and the true last position, so you can hear and see the lag directly. That visible delay is exactly why a state estimator can be preferable to simple smoothing. That lag motivates encoding motion and uncertainty explicitly, so we set up the simplest Kalman state that can represent position and velocity. This example sets up the smallest FilterPy Kalman filter for position and velocity. The sensor only reports position, so dim z equals 1, while kf.x holds 2 state parts, position and velocity. kf.f encodes next position equals old position plus velocity, and kf.h says measurements observe only the position element of kf.x. kf.p starts large to reflect initial uncertainty, and the snippet prints shapes and the initial state, so you can confirm the model is ready to infer velocity from a stream of positions. Next, we make the filter actually trust or question measurements by giving it noise models and running a single predict update step. This code adds the noise assumptions and runs one predict update cycle with FilterPy. kf.r is the sensor noise variance. Bigger values make the filter put less weight on each measurement, while kf.q is the process noise that lets the model deviate from perfect constant velocity. The snippet calls kf.predict to push the state forward, then kf.update with the first noisy reading to fuse observation and motion. The printed covariances show uncertainty before and after the update, and the new kfx demonstrates how the estimate blends the motion model and the measurement. With parameters and a single step working, we run the full loop to collect a tracked history and reveal the inferred velocity. This snippet runs the full FilterPy loop over the remaining noisy measurements. Each iteration calls kf.predict to forecast next position, then kf.update with the new measurement in mies to correct that forecast. The list track accumulates kf.x values so you can later extract estimated positions and velocities. Even though velocity never appears in mies, consistent changes in position force the filter to infer a velocity that explains them under kff. The snippet prints the final estimated position, inferred velocity, and the 1 sigma position uncertainty from the covariance, the exact numbers you'd use in a live tracker. Finally, we turn this into a tiny evaluation so you know whether the filter actually helped. This example turns the FilterPy run into a small baseline you can score. The raw sensor readings in Z are compared with true pause, and the filtered position estimates in EST are compared with the same ground truth. NumPy computes both root mean squared errors and a gain that reports how much the Kalman estimate reduced error on this toy track. The printed error numbers give a concrete sense of improvement, and the reduction in RMSE is the simple metric you would use on log tracking data to choose between smoothing and state estimation. That completes the minimal experiment and gives an objective check. In a real project, you would map true pause to your logged GPS or LiDAR reference and Z to the sensor stream you actually record. The same predict update loop scales to longer logs, and the evaluation pattern translates directly to holdout segments. Summing up, a Kalman filter fuses a motion model with noisy measurements to produce position, velocity, and a quantified uncertainty. Use it when you have a plausible motion model and noisy sensor data, and you want smoother estimates plus a 1 sigma uncertainty to guide decisions. One caveat: the filter only works as well as the motion model and noise parameters you feed it. A concrete next step is to tune the process noise matrix, KFQ, on a held-out segment of your logged GPS track. Grid search KF.Q across a range. Measure RMSE on a validation segment, and pick the setting that reduces error without making the filter too sluggish. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.